Okay, for this problem, we need to determine if we need a free body diagram or not. It's not a dead giveaway, because if you read the problem, we're not being asked for a force or a moment. So we have to count the degree of freedom. The degree of freedom in this case is 1, because if you stop link AB from rotating, then nothing else can move without breaking or bending. So there's 1 degree of freedom. What that means is if I am given 1 velocity, I can find any other velocity that you want. And if I'm given 1 acceleration, I can determine any acceleration without needing a free body diagram. We haven't talked about this too much, but also you notice that it is not a time spanner because they're asking me for the velocity and acceleration at this position. That means I'm not going to be integrating anything. Very few problems because the problems are rather long already. Few problems are going to require integration, but all of the concepts that we used previous are still applicable. Okay, so I know I can do it without a free body diagram. Basically, that all this means is that there's a constraint or a relationship between one motion and another motion. One of the ways to do that, to solve this problem, is to use special points, because that's what that method does, is it relates one velocity or acceleration to another, one motion to another motion. In order to use special points, so I'm going to do it here, and then I'll have another video that will do another method. So if you're going to use special points, one of the first things you want to do is you want to determine how many rotating bodies you have. In this case, I have 2 bodies. One of them is the AB body, which is this mechanism, and the other one is the BC body. Okay, focus on each body one at a time. So look at the AB body. You can call it anything you want, it doesn't matter, but as long as you know what you're talking about. Okay, so on the AB body, you look for the number of special points, and you remember that there are 3 reasons why a point is special. 1, it doesn't matter what order you do them in. 1 reason is you know something about the body, or the point. The second thing is you want to know something about the point. Or 3, the point touches more than one body. Okay, so if you look at all of the millions of points that are making up body AB, there's only 2 of them that are special. One is A, because it's touching the ground and it's touching the link. You also know that there's contact there. You know something about the velocity and acceleration of A. So there's a couple of reasons that A is special. You only need 1. And B is the other point that's special. There are no other special points on body AB. On body BC, there are 2 special points as well. One is B and one is C. Since there are 2 special points on AB, the number of special point equations I write is 2 minus 1. So I'm going to write 1 equation on body AB, and then the number of special points on BC is also 2. 2 minus 1 is 1, so I'm going to write 1 equation on body BC. Okay, so let's do it. So to do write a special point equation between A and B on body 1, you pick 1 point, right? Either A or B. Well, I'm going to choose B. So I start the equation off with the velocity of B equals, and these equations are exactly the same for all bodies, all points, etc. So the velocity of B equals the velocity of the other point, which in this case is point A. So once you choose B on the left, you have no choice but to put A here, if you're going between A and B, right? Plus omega, and you need to know, in this case you have 2 bodies, so what omega is it? Remember that angular velocities, omegas, only apply to bodies. They do not apply to points. So you have 2 bodies, so which omega do you use? Well, you look at the 2 points that are in the equation, A and B, okay? Look at those 2 points. They share a body. What body are they sharing? They are sharing body AB. So I want the omega of body AB. And then you cross it with, and now this R vector is always from the the point that was over on the right-hand side to the point that's on the left-hand side. So it goes from A to, so I'll draw a little arrow, so it's from A to B. It has to go from A to B. Cannot go the other way, plus the VREL terms. Okay? So let's write the second equation. This would be one equation on body BC, or whatever you want to call it, and it's going to be between point C and B. So to start off, you decide, flip a coin. Are you going to start off with B, or are you going to start off with C? In this case, I start off with C. It makes no difference. Just pick one. The velocity of C equals the velocity of the other point. So in this case, the other point is B, plus omega. Which omega? Well, look at the 2 points that this equation is being written for. It's being written for point B and C. Look at B and C. They are sharing a body. What body are they sharing? They're sharing body BC. So it should be the omega of BC. All right. Cross R. R from what to what? It always goes from the point that's on the right-hand side, this one, B, in this case, to the one on the left, C. Right? So that's why it's always R from the right guy to the one on the left, plus the VREL term. Okay, before we go any further, let's just determine values that we're going to put into this equation. So we'll scroll up a little bit. Okay, so what I want to do is find the angular velocity of body AB. So you ask yourself, is it simple? Yes, it is, because it's a two-dimensional problem. Okay, well then the omega is the dot of an angle. How do you find the angle? Well, what you do is you paint a line on the body. Okay, so this yellow line is a good line. And then you paint a line on the ground. Well, here's a line on the ground. Find the angle between those lines. Okay, it's theta. So this would be theta dot is the magnitude of the angular velocity. Now you need to know what direction it is. So since I have to do that, let's find directions. Right? So where do you want the eye? You can put the eye anywhere you want. Most people make it point to the right. So, all right, I'm going to do the same thing. Eye's pointing to the right. Where's the J? The J has to be perpendicular to I. Okay? So it could be up or down or whatever, but most people like to choose it up. So I'm going to choose I to the right and J up. Once you choose the I and the J, the K has to be either out of the paper or into the paper. The way you find out is you take your right hand, you point your fingers of your right hand towards the I, you wave at the J. The J is pointed up, so you turn your fingers up. That's going to force your thumb of your right hand to point out of the paper. Therefore, K is out of the paper. So I know which direction that is. All right, now, back to the omega. In order to find out if this theta dot is in the plus K or the minus K, you pretend that the angle theta is getting bigger. So you look at the diagram. If you look at the diagram, and if theta is getting bigger, I'm not saying it is, but if it were getting bigger, would the link AB be going clockwise or counterclockwise? Well, the answer is counterclockwise. Okay? Curl your right hand fingers in the counterclockwise direction. Which way does your thumb point? It points out of the page. So the omega vector is out of the page. Is the out of the page a positive K or is it a negative K? It's a positive K. So therefore omega AB is a positive theta dot K. Look at the other body, BC. Is the angular velocity simple? Yes, it's 2 dimensions. Okay? We need to find an angle. What angle? Well, you paint a line on the body, right? So this little red line's a good enough line. Paint a line on the ground. Okay, well here's a vertical line. Okay? Looks like it's stuck to B, but anyway, it's vertical. Find the angle between them. Okay? Let's call it beta. The angular velocity is the rate of change of beta. So the angular velocity is beta dot, angle dot. We now need to know what direction. Okay, look back at the figure. Look at the beta. If beta is getting bigger, then the link BC right? Remember, this one here is on the ground and it's vertical. It's not going to go anywhere. If BC moves and beta increases, then the rod BC is got to be going counterclockwise. If beta is getting bigger, BC is going counterclockwise. Curl your fingers in the counter of your right hand in the counterclockwise direction. Your thumb will point in the out of the page. Out of the page is in the K. So the omega BC is also a plus beta dot K. Now let's get the R vectors. Okay, one vector goes from A to B. Right? So if you're standing on A and you want to go to B, you're going to walk a distance in the horizontal direction, and then you're going to turn the corner and walk a distance in the vertical direction. How far will you walk in the horizontal direction going from A to B? Well, you're going to go a distance L cosine of theta. That's how far you're going to go. All right? Are you walking to the right, to the left? When you go from A to B, are you going right or left or up or down? You're going to the right. Right is a positive I. So this is a positive I. Okay? That's the horizontal. Now, you're going to go vertical, right? How far vertical are you going to go? I'm going to walk a distance of L sine theta. That'll be the vertical distance. So you have an L sine of theta. What direction? Are you going up, down, right, or left? The vertical is going up. That's a positive J. See where the J is pointing? It's a positive J. So you put it in as a positive J. Let's get the other R. The other R goes from B to C. So now you imagine you're standing at B and you want to walk to C. You're going to go a vertical and you're going to go a horizontal. So in this case, what's the horizontal? The horizontal is, the horizontal is L sine of beta. So be careful. Look at the diagram carefully. It's L sine theta. That's the horizontal. Did you go right or left when you're walking from B to C? You went right. That's a positive I. So it's a positive I. You go a vertical distance. How far vertically? You go L cosine of beta. That's the vertical distance. L cosine of beta. Did you go up or down? You went down. That's a negative J. So now you have those. Let's get what we know about the velocity of A, B, C, right? So let's plug in what we know for that. Well, what do you know about velocity of A? Well, it may be obvious to you that A is tied to the ground. It's not going anywhere, so its position is never changing. The change in position is zero. That means the velocity is zero. It's always zero. So the change in velocity is zero, so the acceleration is zero. Or you can use the table that I gave you for contacts. Point A is in permanent contact with the ground. Look at the table. The table tells you that the velocity of 2 points that are in permanent contact with each other are the same in all directions. That means that the velocity of A is the same as the velocity of the ground, 0. So I write that down. Velocity of A, 0. Okay. What do you know about B? Nothing. I don't know anything about B. So I'm going to say, well, it maybe has a direction. It has a horizontal and it has a vertical. I have no idea. I think it's going to the right and up. Who cares? If I solve for Vx and I get a negative number, it's going left. So what? If I get a negative for V dy, it's going down. Who cares? What do you know about the velocity of C? Well, the velocity of C has to be vertical, right? It has to be vertical. If you have difficulty with that, ask me in class. I'll be happy to try to describe that. But hopefully you see, oh yeah, it's definitely vertical. All right. So what does that mean? Well, it has a speed. I don't know how big it is, but I think it's going up. Why do I think it's going up? Because I put a plus here. So I'm thinking it goes up. When I solve for this, if I get a negative number on VC, I'm wrong. It goes down, not up. Okay. Now, those are your equations for the velocities, and I'm going to solve those using Mathematica. You can solve them by hand. It's just tedious. So I'm going to let Mathematica do it. They also want acceleration. When you want velocity and acceleration both, I recommend that you start with the velocity first and then you mimic what you did for velocity with the acceleration. Now there's two reasons that you want to do velocities first. One, the most important one, is that what you'll see is that in order to plug numbers into the acceleration, in general, you have to have the velocities. And the only way to get velocities is to solve the velocity equation. So that means you're going to have to solve the velocity first to get the values you need before you can do the acceleration. So you might as well do it first. Second reason, a little less severe, but the second reason is velocity equations have fewer terms, they're easier to think about, and so there's less likely that you're going to make a mistake, right? Accelerations are much more complicated. People don't have good intuition about them, so you should try to avoid them whenever you can, right? Now, by doing the velocities, you mimic those with the accelerations. I'll show you what I mean. Look on the left-hand side. This is the velocity equation that you wrote between B and A. You're going to mimic that. What you're going to do is write an acceleration equation now, and you're going to write it between B and A and B, just like you did the velocity. Okay? You mimic it. On the left-hand side, it starts with VB. On the right-hand side, you're going to start with AB, the acceleration of B. On the left-hand side, you had equals velocity of A. On the right-hand side, you're going to write acceleration of A. On the left-hand side, it was omega of body AB. You're going to have alpha, the angular acceleration of body AB. So you're basically doing, but they're different. On the left, it's omega. On the right, it's alpha. Alpha is the angular acceleration. Then cross R. Notice that the R on the acceleration equation is exactly the same R as on the velocity. Right? You've already got that. And then there's this other term that omega of the body, omega squared R. Right? The VRELs over here, that should have come back. Let me explain the VRELs. To get the VREL for body AB, you pretend like you are standing on body AB. So you pretend like you're standing there, and you look at what's happening. It looks like the link you're standing on isn't moving. Imagine you're standing on the earth. I know you are, right? So if you're standing on the earth, you look around. Does the floor look like it's moving? No. Does the bookcase look like it's moving? No. Nothing in this that's tied to the floor looks like it's moving. Is it really moving? Yes, the earth is turning, so everything is moving, but it doesn't look like it. That's what you want to do. You want to stand there. It's going to look like that link is not moving. Well, if the link's not moving and A is on one end and B is on the other, does it look like A and B are moving? No, it looks like everything else is moving, but not A and B. If A and B are not moving, the REL term is 0. An easier way to think about that is ask yourself, is A fixed to the link? Yes. Is B fixed to the link? Yes. They're on the two ends. They're fixed. They're not going. They're not flying off. Then the REL term is 0. And the same thing is going to apply for BC. Okay. So there are other REL terms that are in the acceleration equation. They are also 0 because of the same reason. Okay. So that's why the acceleration has no RELs. These terms. And then what you do is you mimic the what you did for the velocity for B and C. So instead of VC, it's AC. Instead of VB, it's AB. Instead of omega, it's alpha. Instead of, well, the R is the same. Right? So here's your equation for that one. Okay. Then over here on the left, I decided, what is the omega AB? Do the same thing. What's the alpha AB? The alpha, for two mentions, if it's simple, the alpha is the second derivative of an angle. What angle? Well, notice on the left it's theta. Okay, it's theta double dot. The theta double dot is a positive k. Right? In this case, he tells me that that link is rotating at a constant speed, so therefore this guy is equal to 0. Okay? On the left, I found the omega BC. On the right, I'm going to find the alpha BC. Is it simple? Yes. Well, then it's a double derivative of an angle. What angle? Beta, just like it was on the left. See what I mean by mimic? Okay. Then the r's, I don't need to repeat the r's, they're the same as they were before. Okay, on the left-hand side, I found the velocity of A, it was 0. Well, what's the acceleration of A? 0. Bingo. On the left, I looked for the velocity of B. I said, well, I don't know it. Same thing's going to happen over here. You don't know the acceleration of B. Okay, maybe it's got two pieces. Who knows? And then what did you do for C? Oh, you knew it was vertical. Okay, what do you know about it now? The acceleration is vertical. Okay, so you've mimicked the equations. Now, what I'm going to do is I'm going to plug this in. If you want to do it by hand, ask me in class, and I'll try. It's just going to be time consuming. Okay, so now I'm going to do math. I'm going to pause it until I bring this up. Okay, we're back. What I have showing on the left-hand side is the file where I was writing the equations without all the highlighting and whatnot. I think it's a little easier to look at it that way. And but let's just kind of scroll up here and look at these equations. And what I'm going to do then is on the right-hand side, here is the Mathematica file, which is posted. These things right in here, all the way down from there to there, those commands are in a file called vectors4.nv, which is also available in the Google Drive. And they are typed in, and they just help dealing with vectors. So begin all your problems where you're going to use vectors. Just begin by including that or opening that file, and then executing these statements. You have to execute them. You can't just open the file. You've got to actually execute them. Okay. Now down here, then you start entering in the problem. Okay. So what I did was I came in, and in order to make my typing a little easier, I put in some directions, right? So I have a direction that I'm calling up AB. So over here on the left, up AB is going to point along from the A to the B vector, right? It's going to go upwards from A up to B. So if you notice what I've done over here, that is going to be the cosine of the theta I, cosine theta I, and it's sine theta j, right? Then I have a direction that I'm going to call down BC. So this is going to point down the BC length. That's going to be the sine of beta I in the horizontal, and it's going to be down, so it's negative, cosine beta in the j. Then I have down here, skip ahead a little bit, here's the r's. So here's my r from A to B, and it's simply L times the up AB direction. And if you look at them, that's exactly the same. So the only reason I'm calling up AB and down BC is just to avoid a little typing. And, I think it looks cleaner. It's easier for me to see it and say, yeah, that's right. Okay, so from R from B to C, it's going to be a distance L times this direction, down BC. Okay, the omega of body AB, the author calls it W, and it's in the K. Right, so that's the omega AB. The omega BC, look at the left, it's beta dot, and it's in the K. Right, don't forget your I's, J's, and K's. Right. Velocity of A. What is the velocity of A? It's 0, but make sure you got to make it a vector. So you say 0I, you can say 0J, you can say 0K. You got to put a vector on it so it knows there's 3 zeros in there. The I is a 0, the J is 0, and the K is 0. Velocity of B. Look at it on the left, look at it on the right. See how I did it? VBXI, VBYJ. Don't forget there's a little space in between the word and the I, right? So it knows it's VBX times I. It's not VBXI. Got it? Velocity of C. It's VC, some number, and it's in the J direction. Again, it's not VCJ, it's VCJ. Okay? What's the angle, theta? The theta is not 60 degrees. Right? What's the beta? The beta is 30 degrees. Right? Now, the special points are not good for finding the positions. That's one of the difficulties. So what you have to do is you've got to go in and find out what that angle is. And if you look at it, the author's trying to make it easy because all of the lengths are equal to L. So when this angle theta is at 60 degrees, the slider is even with point A, and it's an isosceles triangle, and all of the angles on the inside are 60, If all the interior angles are 60, beta is 30. So that's how I knew it. I'll show you another way of finding the angle. But you got to find the angles. Nothing has changed here. Okay, so now you have these two vector equations on the left-hand side. So here are my v equations. These are my velocity equations, and there's a set of them. That's why you use a curly brace. If you notice, here's velocity of b equals two equal signs, because it's an equation, equals the velocity of a plus, here's how you do a cross product, cross of omega with r, and the v rel is 0. Okay. Second equation, velocity of c equal velocity of b plus omega cross r. You execute that, bingo, you get this formula here. If you want to pick it out, you can. This is the I on the left-hand side, VBXI. The second term in between commas, that's the J component, and this is the K. Since you're doing 2 dimensions, all the K's should end up being 0. If they're not, you've done something wrong. Here's the I piece on the right-hand side, and here's the J piece on the right-hand side from all of this. Okay? And then here's the second equation. Okay? Alright, then what you do is you solve the equation. So your answer, one equal sign, is equal to v solved is something that I wrote that helps you do a solution of vector equations. What I've found is in previous versions of Mathematica, there was some difficulty solving vector equations, so I wrote my own. What I've seen recently is in the newer versions, it works just fine. You can just say solve. You don't need v solve. But, you know, if solve fails, then try the v solve. Just like the regular solve function, you tell it what to solve. I want to solve the v equations. And then you have to tell it what to solve for. Well, you have 4 equations. You have the i's equal to the i's of the first one, the j's equal to the j's of the second, and then the k is 0 equals 0, so you have one there, but it doesn't help. And so you have two equations for the first equation, and you have 2 for the second, so that's a total of 4. So you have to tell it 4 things you want to solve for. So you want to solve this thing for VBX, VBY, VC, and beta dot. You hit execute, and kabang, you end up with the solution that's shown here. Okay, so now that you have the velocity answer, we want to go find the accelerations. So all I'm going to do is I've already mimicked this, right? So what is the alpha AB? The alpha AB is 0. What's the alpha BC? Beta double dot. Notice there's 2 D. DD dot, right? Double dot. What's the acceleration of A? Nothing. It's 0. Don't forget the I, right? What's the acceleration of B? I don't know. 2 pieces. What's the acceleration of C? I think it's AC up. Okay? So that's what I had over here on the left-hand side. Here come your acceleration equations. The acceleration of B equals, because it's an equation, acceleration of A plus cross product between alpha cross R. Okay, now this is the easiest way I know to find omega squared, right? Just do a dot product between the 2 omegas. It's the same one. Omega AB, that'll get you omega AB squared times RA to B. Okay? So the acceleration of C equals acceleration of B, right? I'm just copying the equation on the left, minus omega squared RB to C. You could just type this in OMBC if you want to, but I find that the easiest thing. Then you hit execute, and here's what your equations look like. Alright? I need to solve it. What do you want to solve? This time you want to solve the acceleration equations. For what? 4 unknowns. Now, when I say mimic it, that's what I mean. Which 4? Well, I mean, they're ugly. I don't know what to solve for. I can't tell. Well, okay, then look back here. What did you solve the velocity for? VBX, okay. Then put ABX instead of VBX. That's what I mean by mimic, right? What did you do up here? You solve for VBY? Okay, solve for ABY. What did you do up here? You solve for VC? Okay, solve for AC. What was the last one? You solve for beta dot? Okay, this time You solve for beta double dot, right? The point is that in general, you never solve the A equation, the acceleration equation, for a velocity. You don't do it. You solve the velocity equation for velocities, the acceleration equation for accelerations. That's why you have to do the velocity first, because you need the beta dots and those things. Okay? So you solve it, and you get this mess here, right? And if you notice, you got a beta dot. Where in the world are you going to find beta dot? Oh, you solve for beta dot from the velocities. Here it is, beta dot. You always get your dots, your single dot terms, from the velocity equation. So I've already solved that. So what I want to do is I want it to put in the solution it got for the velocity into the acceleration. Now you can pull out your pocket calculator if you want and do it. Or this is the way to do it. You say, show me what the A answer is, and substitute in. That's, you say divide in period. It's weird, I know. You say divide in period. That means substitute into that what you have for the A and S, the answer. If you look up here, see, A and S was the name of my velocity answer, right? So what I'm asking it to do is to show me what the acceleration answer is by substituting in the velocity answer, okay? And then what do you have? And there's the solution. So the acceleration of b in the x is a negative. Aha, it's going, I thought it was going right. It's not, it's going left. The acceleration of b in the y, I thought it was going up. I'm wrong. It's a negative. It's going down. The acceleration of c, it's a positive. I thought it was going up. I'm correct. It's going up. What's the beta double dot? I thought it was counterclockwise. You're right. Why? Because it's a positive. I'm right. It's going counterclockwise. Okay? That's it.